some derivative formulas, some rules. What are these? Let's start with the easy one. Start at the bottom. What's that? Okay, how do we say that, by the way? The derivative with respect to x, right? How come? Because we're differentiating with respect to x. That's our input variable. Whatever variable shows up in the bottom there, right, is going to always be the variable. That's the independent variable or the input variable. So the derivative with respect to x of c, where c is just some constant, is 0. Yep. The derivative with respect to x of cx is c, right? Yep. Okay. And the derivative with respect to x of c times x to the n would be what? Okay, but we have that c out front, so... Okay, good. So c times n times x to what power? N minus 1. Good. All right. Good, good. Okay, so here's the only thing I want to do today. I want to calculate the equations of a tangent line and a normal line. So we know what a tangent line is, right? Are you guys off? Where are you today? Gladstone. Okay, there you go. All right. Well, beat Gladstone. See ya. Okay, so we know what a tangent line is, right? The slope of the curve at a point, right? So a tangent line is that point that grazes the curve at the point of tangency. What's a normal line? Normal is a really important word in math. No. I'll give you a hint, it's related to the tangent line. So as the tangent line changes, I mean, not exactly. So the normal line just means perpendicular to. So if the tangent line is parallel to the curve at a point, the normal line is the one that's always perpendicular to the curve. So in other words, it's perpendicular to the tangent line at the point of tangency. Okay? So that's important because when you start to expand calculus, we're doing calculus of a single variable, but in college you guys will do multivariable calculus, where you might be talking, instead of looking at tangents to a two-dimensional curve, you might be looking at tangents to a surface, right? So think like a topographical map, one of those relief maps where you've got mountains and valleys and things. So if you wanted to, look at like a tangent line to a surface, then you'd be finding the line that is parallel along a certain direction to a surface. And you might be looking at things like parallel planes even, right? Like the plane that's parallel to the surface at a point. So think about taking a piece of cardboard. Does that make sense? And so then the normal line is going to be the line that is perpendicular to that plane. Okay? Right? And so as you move along a surface, that plane of tangency and the normal line would be changing as you move along that surface. So that's what you've got in your future coming up. And the good news is, once you've done calculus of a single variable, extrapolating to more variables isn't really that big a deal. I mean, you're just taking the same concepts and you're just expanding them with some other concepts. There's some mechanisms for dealing with, for example, if we have like a function, a surface that's got, let's say, x and y values as a function of, you're going to output z's, right? So in the plane, you're going to be looking down from above on this map, but at a certain point there's going to be a z value that gives you the elevation above, like sea level of the, right? Anyway, you'll get there. But that stuff, it's not that much of a change from what we're doing now. Got to learn this stuff first, though. So we're dealing with tangents and normals just in the xy plane, which makes it a little bit easier. Okay, so how would I find the normal line then? What's your strategy going to be? Exactly. That's all you're going to do. Once you find the tangent line, the normal line is easy, right? Because the point is going to be the same point. The point of tangency is still the point that we're going to use to define the normal line. The only difference is the slope's going to change, right? But that's easy. If we can find the slope of the tangent line, the normal line is just perpendicular to that. And how are the slopes of perpendicular lines related again, going clear back? Yeah, just opposite reciprocals, right? So really, finding the tangent line is all the work. The normal line is trivial from that point. You've already done the work. Okay, so let's do this then. Let's find the equation of the tangent line first. So again, what are the ingredients of a line? Point and a slope, yeah, okay. So let's see, we've got our, they tell us x equals 2 is the place where we're trying to find the equation of our tangent line. So how would I find a point there? I know the x value. Plug it in, sure. Okay, so y just equals f of 2, which is what? 2 plus 1/2, so 5/2. Okay, so we have a point of tangency then at 2 5/2. How am I going to find a slope? Okay, yeah, so right, so now we're going to have to do, say it again, a slope. How am I going to find a slope? You guys are jumping ahead. Derivative, right? Okay. So the slope of the tangent line is going to come from the derivative. In order to find the derivative, we need the derivative function though. Okay, so I want to calculate f prime. But before I do that, I need to pre-write this function, because it's not really written in a form where I'm able to see what the derivative is. Eventually you'll just do this in your head, but for now let's be a little more explicit about that. How could I rewrite that in a way so I could differentiate it using just the few rules that we have? I've got two terms, but that's not a problem because I just differentiate term by term, right? So that's not a big deal. The first term is fine, but what am I going to do to that second term? What am I going to do? X to the -1, right? Yeah. We'll just write this as x to the -1, and now I can use my power rule, right? My generalized power rule. Okay, so what's f prime going to be then? We pre-wrote this, so now we can differentiate. What do we get? What do we get from the first term? What's the derivative of x? Well, derivative of x to the 1 is 1. Right? Derivative of x is just 1. Derivative of x with respect to x is 1. How about this one? Use your power rule. What are we going to do there? What do we do if I'm to the -2? Exactly. Bring the exponent down so we get a -1 in front, and subtract 1. So we just get that. Well, if I write that, maybe it's more convenient to write that in that form. Okay? So the slope of the tangent line then, what would I have to do to find the slope of the tangent line? How am I going to use my new derivative function that I just calculated? Yeah, so I'm evaluating it at 2, right? The slope of our tangent line is just going to be f prime of 2. Okay, give me thumbs on that. Does that make sense? How we're getting that? Okay. And then we can evaluate that. So that's just what? 1 minus 1/4. Everybody agree? 1 over 2 squared equals 3/4. And this is no big deal. Now we've got a point, we've got a slope. We're there, right? So the slope of the tangent, or the equation of the tangent line would then just be y minus 5/2 equals times the quantity. There it is, right? Piece of cake. And that's my tangent line. And I could just solve for y, right? And we won't even bother, but that'd be no big deal. I just distribute the 3/4 and add 5/2 to both sides, and we got it. Okay, how could I do the normal line? Yeah, everything's the same, isn't it? It's the same point. The only difference is for our slope, we're just going to need the opposite reciprocal. So it would just be y minus 5/2 equals negative 4/3 times the quantity x minus 2. That's it. Okay? Make sense? All right. You got to do a little bit of that on the assignment. I'm going to let you work.